This problem looks very scary. We've got a giant summation here in this condition, but using our techniques, we'll figure out a way to break this scary problem down into something a lot simpler. Let's see what this problem is about. We've got x0 through something be a sequence of numbers, where x of k is either 0 or 1. For each positive integer n, define s of n to be the sum from k equals 0 to n minus 1 of x to the k, 2 to the k. Let's stop right there. 2 to the k, x to the k, 0 or 1. This should remind you of something immediately. Each digit is 0 to 1, 2 to the k we're multiplying by. That looks a lot like binary. So S of n, so let's break down what the summation is, because understanding in summation notation is much harder than seeing what it really is. So for k equals 0, it's x of 0, 2 to the 0. For k equals 1, it's x of 1, 2 to the 1. For 2, it's x of 2, 2 squared. For 3, it's x of 3, 2 cubed, and so on, as you can see, all the way till n minus 1, 2 to the n minus 1. And this is S of n. So what is this in binary? If we express this number in binary, because each of xk is only 0 or 1. So if we express in binary, we can see that there are n digits. Why are there n digits? Because there's n different powers of 2. 0 to n minus 1. There's n powers of 2, and each are being multiplied by 0 or 1. That's a binary number. So S of n equals this binary number, x of 0 all the way till x of n minus 1, for a total of n digits, right? Because there's x to the n minus 1 to 0, there's n of those x's that make up S of n. Okay, now we've got this condition. 7 S of n is 1 mod 2 to the n. What does that mean even? Well, S of n is the sum, and 7 times that is 1 mod 2 to the n. But how do we even use such a weird condition? I mean, I thought we were doing binary here. Where did modular arithmetic come from? Okay, so what we're going to do here is see that what are the possibilities where 7 times the sum is 1 mod 2 to the n. Okay, let's write this systematically. First case is S 7 times S of n could be equal to 1 itself, right? The second case is 7 times S of n is 2 to the n plus 1, right? Because it's 1 mod 2 to the n, you can add multiples of 2 to the n, and this could be the value of 7Sn. Essentially, 7Sn could be 1 plus 2 to the n plus some multiple of 2 to the n. So it could also be 2 times 2 to the n plus 1. It could also be 3 times 2 to the n plus 1. Or 4 times 2 to the n plus 1. 5 times 2 to the n plus 1. 6 times 2 to the n plus 1. Now we can keep writing forever. There's going to be infinite possibilities, but where do we stop? Well, remember, what is S of n even? Remember, it was a binary digit. It was a binary number with n digits, where each one is 0 or 1. Wait, but don't we know that the maximum value of S of n, remember, x could be 0 or 1, all of the x of k's. So even if all of them were 1, we would have 1 times 2 to the n minus 1, plus 1 times 2 to the n minus 2, all the way till plus 1 times 2 to the 0. And this is just, well, geometric sequence formula, this is 1, or just 2 to the n minus 1. And basically, this number is always less than 2 to the n. Another way to see this is that if S of n was bigger, was 2 to the n or bigger, it would have n plus 1 digits in binary, And it would need a digit for the 2 to the n coefficient. You know how we have digits for 2 to the n minus 1, n minus 2, so on, and to 0, but we don't have one for n. Essentially, if the number was 2 to the n, it would be 1 with n zeros in binary. N zeros. So it would have n plus 1 digits. So that's not possible with our n digits. So we know that 2 to the n is bigger than s of n. And that means, well, is this possible even? Well, like we deduced earlier, s of n is less than 2 to the n. So that means 7 s of n is less than 7 times 2 to the n, which is also less than, that also means 7 s of n is less than 7 times 2 to the n plus 1. And that same thing is going to be true if this was an 8. If this was an 8, or a 9, or a 10, or 11, or whatever it would be. Anything bigger, that's too big. So, this is it. These are the only possibilities. But even all these, not all of them work. Let's see which ones do work and which ones don't work. Okay, first of all, 7 of s of n equals 1. S of n is an integer, right? We're adding up powers of 2 times an integer. Can an integer times 7 equals 1? Well, this would mean s of n is 1/7. Obviously not possible. Okay, the second case. S of 7 times s of n is 2 to the n plus 1. So this is, remember, s of n is an integer. So for s of n to be an integer from this equation, we must have 2 to the n plus 1 be a multiple of 7. Because if this wasn't a multiple of 7, then neither would s of n wouldn't be an integer, because we're multiplying by 7 on this side. So this is possible only when 2 to the n plus 1 is a multiple of 7, or 0 mod 7. And we can rewrite this as is congruent to negative 1 mod 7. What are powers of 2 mod 7? Well, let's take a look. 2 to the 0 is 1 mod 7. 2 to the 1 is 2 mod 7. 2 squared is 8, 2 squared is 4 mod 7. 2 cubed is 8, which is 1 mod 7. 2 to the 4 is 2 cubed times 2, which is 2 mod 7. And so on. We just keep multiplying by 2 to the mods. And as you can see, it cycles. 1, 2, 4. 1, 2, 4. But remember, negative 1 is just 6 mod 7. It's the same thing. Oh, but if it cycles from 1, 2, 4, 1, 2, 4, it's never 6 mod 7. So that means this case is impossible. Boom. Doesn't work. Because this will never be a multiple of 7. Okay, this one here. 7 s of n equals 2 times 2 to the n plus 1. So for this to happen, we must have, like I mentioned earlier, for s of n to be an integer, this will be a multiple of 7, which means this side also has to be a multiple of 7. So we must have 2 times 2 to the n be plus 1 equal 0 mod 7. And we can subtract 1 from both sides. We get this is equal to negative 1 mod 7, which is also the same thing as 6 mod 7, if you'd like to write it without negatives. And now, we can see that for 2 times 2 to the n to be 6 mod 7, well, 2 times 1 is 2 mod 7, 2 times 2 is 4 mod 7, and 2 times 4 is 1 mod 7. So the only possibilities for this quantity here, mod 7, is 2, 4, and 1. It can never be 6. Another way to see that, if you found that confusing, is to see that we can divide by 2 from both sides to get that 2 to the n is 3 mod 7, which is obviously impossible as well. And the reason we can divide by 2 is because 7 is relatively prime to it. So, this case, also fails. Now we're on to the next case. Okay, what about if this is equal to 3 times 2 to the n plus 1? Similarly, we must have 3 times 2 to the n equals -1 or 6 mod 7. And that means 2 to the n equals 2 mod 7. And just to be clarification here, we can divide by 3 in this case because 3 is relatively prime to 7. But if you had something like 6 mod 10, we had something like 2x is 6 mod 10. Now you can't just divide by 2 and get x equals 3 mod 10 because you can only divide by things that are relatively prime. For example, 8, if you plug in 8 here, this would give 16. So look, 8 mod 10 numbers do work. Like 8 does work because 2 times 8 is 16, which is 6 mod 10. So just to be clear here, you can only do division like I'm doing here if the numbers are the number you're dividing and the mod are relatively prime, which they are in this case. Okay, so 2 to the n is 2 mod 7. Oh, that happens here. And here. Aha! Or it happens in 1, in 4, 2 mod 7, 2 mod 7. And it will happen. So when does this happen then? It happens when the exponent is 1 mod 3. It happens when n is 1 mod 3. Why? Because as you can see, 2 to the 1 works, right? And if you multiply this by 2 cubed, it also works, 2 to the 4. You can multiply it again by 2 cubed, 2 to the 7. Then 2 to the 10. So on. Basically, we keep adding 3 to the exponent, we'll keep getting 2 mod 7 numbers. So for all values where the exponent is 1 mod 3, 2 to the n is 2 mod 7. Okay, that's cool. So we know this one does work. It's not a cross out like the other ones. We'll put a big check here. Let's take a look at the next case. We do the same standard drill. 4 times 2 to the n is 6 mod 7. And in this case, we can't just divide by 4, of course, because that would leave this side being 1.5. But the key thing to see here is that this left side is equal to 6 is equal to 20 mod 7, right? Because 20 leaves a remainder of 6 when divided by 7. So they're equivalent. And now we know that 4 times 2 to the n is 20 mod 7. So we deduce that 2 to the n is 5 mod 7. Is this possible? Do we have a 5 here? Nope. So we're going to cross that one out. Okay, so far we only have one case that works. Are there going to be any others? Let's find out. This over here. 5 times 2 to the n is 6 mod 7. And the trick here is we just keep adding multiples of 7 to 6 until we get a multiple of 5, and then we divide by 5. So 6 plus 7, 13. 13 plus 7, 20. So, it's equivalent to 20 mod 7. And now we can divide by 5 without having fractions. So 2 to the n is 4 mod 7. Is this possible? Of course it is. It happens when the exponent is 2. It happens when the exponent is 5. It will happen when the exponent is 8. Because it cycles every 3 powers. So it happens when the number is 2, 5. It basically happens whenever the exponent is 2 mod 3. So we're just going to draw an arrow here. And this one here and here. Okay, final case. This one here. And this is the same standard drill. 6 times 2 to the n is 6 mod 7. Which gives 2 to the n is 1 mod 7. And this happens when, look here, 0, 3. And it will happen at 6, 9, etc. It cycles every 3 powers, so it's just going to be all numbers where the exponent is divisible by 3 or where the exponent is 0 mod 3. Wait, so basically, if we have that this equation is true, this one right here, when n is 0 mod 3, right? Because we just found that when this is divisible, we have n is 0 mod 3. And over here, we found that 7 times Sn is 5 times 2 to the n plus 1 when n was 2 mod 3, right? And we found that this equation was true when n is 1 mod 3. We've covered all possible values of n mod 3. Okay, let's write what this means. So if n is 0, if n is 0 mod 3, right? We found that n was 0 mod 3 when this equation is true. So n equals 0 mod 3 means that this equation must be true. Because for n equals 0 mod 3, none of these other quantities are 0 mod 7. So therefore, we have 7 Sn equals 6 times 2 to the n plus 1. If n is 1 mod 3, just like we found earlier, because we found that this side is only a multiple of 7 for n 1 mod 3 in this equation. So this is the equation that must be true, right? Because none of these other ones will give a valid Sn, an integer. So for n equals 1 mod 3, it's 7 Sn equals 3 times 2 to the n plus 1. And finally, we have that for n equals 2 mod 3, like we found down here, that by similar logic, this equation is the only one true. 7 Sn equals 5 times 2 to the n plus 1. So we can divide. Let's take a look. Let's start back here. So that means that S of n is 6 times 2 to the n plus 1 over 7, which we know is an integer, right? Over here, we have S of n is 3 times 2 to the n plus 1 over 7. And again here, same thing, 5 times 2 to the n plus 1 over 7. Okay, let's go back to what we're looking for. We're looking for the sum of x values. Wait, x values? We have s values. Okay, so we have to somehow convert from s to x values. Okay, notice how I kind of wrote these digits, those digits over there, over here. Let's write them again. So we know that, okay, maybe not, let's just continue working over here. Right? So the key thing here is that is the value of S of n, this quantity up right there. What about S of n minus 1? Well, that's something very similar, except because we only have n minus 1 digits now, it only goes from x of n minus 2 down. Remember how here for S of n, we start at x of n minus 1, but for S of n minus 1, we start at x of n minus 2. So, well, what happens when we subtract them? Well, the key thing here is when we subtract them, almost all the terms cancel out. X of 0 cancels out, x of 1 cancels out, x of 4 cancels out, x of 3 cancels out. Or this should be x of n minus 3 here, not minus 1. X of n minus 3 cancels out, x of n minus 2 cancels out. The only thing left is this digit here, x of n minus 1. So we have s of n minus s of n minus 1 equals this digit x of n minus 1 with some zeros, with n minus 1 zeros to the right of it. Because there's n minus 1 digits here, right? N minus 2 minus 0 plus 1, you know the counting formula. So there's n minus 1 digits to the left of x of n minus 1, so it's x of n minus 1 times, well, 2 to the n minus 1. Okay, that's cool. Oh, but remember, this quantity must be a 1 or 0. So that means we have that. Let's erase this part because we already know what our values are that work. We have that x of n minus 1 equals, or s of n minus s of n minus 1 over 2 to the n minus 1. And instead of n minus 1, if we now put x of n, we just increase all of these coefficients by 1. So s of n plus 1 minus s of n over 2 to the n. right? So then what values will x of n become, will x of n become 1, and what values will it become 0? Well, we know the formula for calculating s of n, so right here, we found our formulas. So we just have to plug those in. Okay, so let's take a look case by case. Because as you can see here, they're different from mod 3. So if n is 0 mod 3, then x of n equals s of n plus 1 minus s of n over 2 to the n. And n plus 1 will be 1 mod 3. So then it will have the formula right there. 3 times 2 to the n plus 1 over 7. And it's n plus 1, so 3 times 2 to the n plus 1 over 7 minus s of n, which is just this formula, 6 times 2 to the n plus 1 over 7. And if we evaluate this, we notice that 2 to the n plus 1 is just 2 to the n times 2. So that means 3 times 2 to the n plus 1 is the same as 6 times 2 to the n. So if we subtract these, all the terms will cancel out. 1 will cancel, and this term will cancel. We're left with 0. So for n equals 0 mod 3, x of n is 0. Now what about here in this case? N is 1 mod 3. Then x of n equals, same thing, s of n plus 1 minus s of n over 2 to the n, which is, well, in this case, n plus 1 will be 2 mod 3, so it will have this formula. 5 times 2 to the n plus 1 by 7 minus the formula for s of n is just this quantity right there, minus 3 times 2 to the n plus 1 over 7, all over 2 to the n. Okay. We can find a common denominator, of course, and that becomes minus 3 times 2 to the n plus 1. The 1's cancel. And this quantity right here, we can rewrite it as, because 2 to the n is 2 times 2 to the n, 2 times 2 to the power of n, right? We can make this 2 to the n, 5 times 2 to the n plus 1, 10 times 2 to the n. And then if you evaluate this, 10 times 2 to the n minus 3 times 2 to the n, that's 7 times 2 to the n. So this is 7 times 2 to the n over 7 over 2 to the n, and this is 1. Okay, that's cool. And a shortcut here is you can see that this quantity is positive, it's not 0. And x of n is 0 or 1. So if it's not 0 and if it's positive and it's not 0, then it has to be 1, because it has to be 0 or 1. So there's no need to actually evaluate this. So similarly here, let's see what we have. S of n, okay, so we know that our formula again, x of n is s of n plus 1 minus s of n over 2 to the n, right? S of n plus 1, s of n plus 1 is just, well, n plus 1 is 0 mod 3. So s of n plus 1 will be 6 times 2 to the n plus 1 over 7 minus s of n for n equals 2 mod 3, which is just 5 times 2 to the n plus 1 over 7. And then we divide all of this by 2 to the n. So like I was mentioning earlier, you can actually evaluate this and you'll get that it's equal to 1. It's not too hard algebra. I'm sure you can do it. But the other way is just to see that this is positive, of course, right? This quantity is bigger than this quantity, so this is a positive number. And we know that this must be 0 or 1, right? Because x of n is given to be 0 or 1. And it's not 0. It's not 0. And it's 0 or 1, so then it has to be 1. So you can do that two ways like I mentioned earlier. So then x of n equals 1 in this case. So as you can see, x of n equals 1 if n is 1 or 2 mod 3, but not if it's 0 mod 3. Now looking at our problem, we see that x of this quantity is 0, right? Because x of 2019 is a multiple of 3. Similarly, 2022 is a multiple of 3, so that's 0. But these quantities are 1 and 2 mod 3. So x of 2020 is 1, x of 2021 is 1. This is 2 plus 4 equals 6. Our answer, A. Let's recap. So basically, this was a lot. I'm sure it was. The big thing was to see the binary. And then once we saw the binary, we noticed that this condition means that one of these expressions must be true. And if one of those expressions must be true, we looked at the values mod 7 and found that for each value of n mod 3, we found a specific formula for s of n. And then by subtracting s of n minus 1, we figured out a formula for x of n. We applied them for all three mods. We got 1, 1, 0, where it's x of n is 0 for multiples of 3 and 1 for everything else. We plugged it in to get 6. Now, an alternative way of doing this is just to see that this is 1, 2, 4, 8. So this is just equal to s of 20, 23, right? S of 2023 minus S of 2019. Yeah. Because S of 2019, if we rewrite it here, let's clear this page. S of 2023 will include all the digits from x of 2022, x of 2021, so on. And x of 2019, this is S of 2023, x of 2019, x of 2018. S of 2019 is x of 2018 and x of 2017, so on. So if we subtract them, all these terms will cancel, and we're left with this number in binary, just this part. And we'll see that the part over here is just 8 times x to the 2022 plus 4 times x to the 2021 plus 2 times x to the 2020 plus x of 2019. So if it's just the sum of those quantities, then that's exactly what we're looking for here. And that's, of course, going to be times 2 to the 2018 for all of these zeros, all these empty digits on to the right of it. And so this would just be this divided by 2 to the 2018. That would give the exact same answer. So both ways work, and that was a great problem. Thanks for watching.